Well, hello, everyone. Welcome back. This recording is brought to you by Wes Baxter. I'm a math faculty member at Nashville State Community College, and I'm pleased to bring this short presentation to you. We're going to be talking about the compounding of interest in this video. However, we are not compounding the interest continuously like we have seen in a previous video. This particular recording is looking at problems involving the compounding of interest, but it's being compounded periodically. Okay, so it's not continuous compounding, it's periodically done. So, you know, those types of problems are where you compound the interest daily, perhaps monthly, or semi-annually, or quarterly, or it could be weekly or annually. So there's different periods that you want to be aware of. The purpose of this video then is to help students understand how to solve interest-related problems that do not involve continuous compounding. We're going to see that there is a specific formula that you can use for these particular types of problems. And we're going to just look at the algebraic approach in this recording. There will be a separate recording where we look at these types of problems, but I'm going to focus on the graphical approach. And I really want to encourage you to watch that video, because understanding those graphical approaches just really helps you to understand functions better in general. And you will become better at just analyzing functions, and you can take that knowledge with you to future math courses. And perhaps it will help you on the final exam in this particular course. So really take a look at those recordings that we put out there for you guys. Here's a sample problem. Jamaica invests $10,000 in an account that pays 4.5% interest that is compounded monthly. How long will it take for the account balance to reach $25,000? Notice in this problem, it does say that the interest is compounded monthly. Okay, so it does not say that the interest is compounded continuously. Now, if it did say that it was compounded continuously, then there is a particular formula that you would want to use for that type of problem. But this one says that it's compounded periodically, and the period is monthly. Okay, so look for those problems specify that it's being compounded periodically. When you identify those types of problems, then there is a specific formula that you want to use to solve those types of problems. And here it is. So the formula is A of t equals P times 1 plus R divided by N, and that quantity is raised to the N times T power. Okay, so this looks very familiar to the previous formula that we used when compounding continuously, but notice it is a different formula. They're not the same, but the notation that's used is very similar. So let's talk about each piece here. A of t, now that represents the future value of your account balance. So this is the account balance after some time t has gone by. So that's what this A of t represents. That's your dependent variable. And then on the right side of the equation, we have P, which stands for the principal. That would be the present value of your investment. That's the present value of your account balance. All right, so that would be what you're investing today. So for example, Jamaica is investing $10,000 today. So that's going to be the principal 10,000. And we're looking for it to increase to 25,000. So 25,000 would be the future value. All right. So we have the principal times 1 plus, and then we have this R over N. R for the interest rate as a decimal. Okay, so don't forget, the problem will likely give you the interest rate as a percentage. You always have to change that percentage to a decimal, okay? And then once you have the decimal, that's what you put in here for the R. And then that's divided by N. Now, N is the number of times that you compound the interest, sorry about that, per year. Okay, so N, in this case, in this example, will be 12 because we're compounding the interest monthly, and there are 12 months per year, okay? If it said quarterly, for example, there are 4 quarters per year, and then in that case, the n would be 4. Okay, so both of these n's would be 4. But in this particular example that we're looking at, it's compounded monthly, so there are 12 months per year. So the n will be 12. So both of these are 12. And then in the exponent, the n here is being multiplied by the t. The t represents the time in years. So here's the sample problem again that we're working with. Now let's see how this works algebraically. So let me switch screens here just for a second. Takes just a few seconds for this to switch over. Right, there we go. So what I want to do, all right, so when I read this problem, again, the key phrase that I caught on to was that the interest was compounded monthly, okay? So immediately I can know that I can use this particular formula for those types of problems. And again, the formula is A of t equals P times 1 plus R divided by N, and then close parentheses there, and then that's raised to the N times T power. I just need to plug everything in that I know. In this example, I'm going to be solving for the T right there, because that's the only thing that I don't know. Plus the question says, how long will it take for the account balance to grow to $25,000? So it's asking about the time that it's going to take to grow to that amount. So that's what I'm solving for. So let me plug everything in. So the future value is 25,000. As we discussed before, the P is going to be the 10,000 because that's today's investment. That's what Jamaica is investing right now today. And that is being multiplied by 1 plus the interest rate we're going to put in as 0.045. It was 4.5%, but you change the percent to a decimal. So that decimal gets taken back to the left 2 spaces. That's going to be divided by 12 in this example. And then, oops, I was going to write n, but n we know is 12 in this example, right? So plug in 12 and then times t. We don't know the t just yet. The next thing I want to think about is the type of equation that this is. So I'm trying to solve for the t. And notice the t is up there in the exponent. Okay, so when your variable is in the exponent, then you know that you've got an exponential equation. So this is an exponential equation. And to solve exponential equations, you must somehow get that exponent down so that you can work with it. And the only way that you can get that lowered down where you can work with it is by taking a logarithm. Okay. So let me just kind of demonstrate. Now, the first thing we'll do is let's work inside the parentheses. Okay, so I'm kind of thinking about the order of operations. So let's work inside the parentheses there. And let me just kind of simplify that part before I jump into the rest of it. When looking inside the parentheses, I would want to work with this fraction here first, okay, because the order of operations says that division would come before addition. So I want to go ahead and take care of that division. So let's do 0.045 divided by 12, and then I just hit enter. And so that's 1 plus, that fraction is 0.00375. Now I just rewrite everything else. And then of course 1 plus 0.00375 is going to be 1.00375. So let me just write that. Times 1.00375. And that's raised to the 12 times t power. Okay. Now that I have simplified what was inside parentheses, in order to now solve for the t up there in the exponent, I want to isolate. So you always want to do this. You want to isolate the base. The base here is the 1.00375. Isolate that base along with its exponent there. So to isolate that, I'm going to need to divide by 10,000. So I need to divide both sides of the equation by 10,000. Whatever you do on one side, you must do the same thing on the other side. So those 10,000s will cancel. And then what I have remaining is 1.00375 raised to the 12t power. And then we know from a previous video that 25,000 over 10,000, this fraction on the left, that just reduces down to 5 over 2. All right. Now, I've got the base and its exponent isolated on that one side. So now what I can do to bring that exponent down is I'm going to the logarithm of both sides of the equation. Okay. So whatever you do on one side, you must do the same thing on the other side. So you take the log of both sides. And we do that, guys, what that allows us to do, according to the power rule of logarithms, I can now move this power, this exponent out front of this logarithm, and I can rewrite this expression on the right side as a product, okay? So I can rewrite this as 12t times log 1.00375, okay? Which is awesome because now I can easily solve for the missing t. So I'm wanting to get the t by itself. So what I have to do is I've got to divide. You know, everything's being multiplied there. So to get rid of things that are being multiplied, you have to do the inverse operation, which is division. All right, so to get rid of the 12, I need to divide by 12. To get rid of the log, I need to also divide by that log. I'm just going to do both of those things in one step. Okay, and then I do the same thing, of course, on the other side. So I'm dividing by 12 times log 1.00375. Okay, and so the 12s cancel and those logs cancel on that side. And that leaves me with just the t. And so I now know that the time required is this log of 5 over 2 divided by 12 times the log of 1.00375. Okay. So now what I would do for something that's sort of a complex fraction, kind of a complicated fraction, I want to actually figure out what the numerator is. So I'm just going to, I've got my calculator here. I'm not going to show it to you on the screen just now because that requires me switching my screens. But I'm just going to type this into my calculator. I've got log and then type in 5 divided by 2. All right, and then I'm actually going to write down that result. And so I'm getting that result for the numerator there. So that is equal to 0.3979400087. So I take that decimal all the way out. And then that's divided by this 12 times. Now on the calculator, you do have to hit times, okay? So, we don't write the little time symbol in between there, but it's understood that you're multiplying, okay? So you have to tell the calculator that you are multiplying. So I want to say 12, I hit the times button, and then log 1.00375. And I'm going to write down the result for that denominator. So there it is. And then the last step is I'm going to actually now divide this out. So I'm going to type in 0.39794000087 divided by 0.0195066,994. And then I've got that the time then is approximately 20.40 years. The time is in years with this formula. Okay. So notice that the time that it takes, this is very similar to the sample problem that we saw in a previous recording dealing with the continuous compounding of interest. Make note that the time required is just a little bit more with the interest being compounded monthly as compared to the time that it took when the interest was compounded continuously. All right. So basically, with all other things being equal, the number of times that you compound makes a small difference in the total outcome of your account balance. For example, if we took the same problem and we found out the time that it would take if you compounded daily, it would take just a tiny bit less time to get our account balance up to $25,000 if we were compounding daily compared to monthly. Okay, so the more times you compound, the less time it takes to reach a certain goal. Okay, so it's, with all else being equal, it's always best to have an investment where the compounding is occurring more frequently. Okay, so the continuous compounding of interest is going to help you reach your account balance goal a little faster than the periodic compounding of interest would. I hope that makes sense. All right, guys, let me switch my screen just real quick. So let me, I do want to just show you real quick on the calculator how we did those calculations, just in case you may have gotten lost on the calculator there. So first, what we did was, we had this expression, we had log, and there's the log button right there on the left. So we had log 5 divided by 2. All right, and then I just hit enter, and that was the number that I had in the numerator. All right, and then I'm going to clear that. The number that I had in the denominator was the 12 times, see, I'm hitting times right there, and then log 1.00375. Close the parentheses around that since it opened parentheses, and then press enter for it to calculate that. And so there's our denominator value. All right, and then once I got the numerator and denominator, what I did is I just typed that out and then divided. So I put in 0.39794000087, and then divided by the denominator, 0.01950669994, and then press enter. And there's the 20.40 years. Okay, thank you very much. So be looking for additional videos, and we will see you there. Thank you.